Formulae of kinetic theory of gases. Formulae of kinetic theory of gases. Number 1. Assumptions of kinetic theory of gases. Assumptions of kinetic theory of gases. Number one assumption is molecules of a gas are in a state of random rapid motion. The molecules of a gas are in a state of continuous rapid and random motion. Continuous rapid and random motion. The molecules, that means they move in all the directions. They move in all the directions with different speeds ranging from 0 to infinity. They move in all the directions with different speeds or velocities ranging from 0 to infinity. Ranging from 0 to infinity. This is the main assumption of kinetic theory of gas. Molecules of a gas are in a state of continuous, rapid and random motion. They move in all directions with different speeds ranging from 0 to infinity. Number 2 concept is cause of pressure exerted by a gas. We can draw the wall of a container of gas. M is the mass of one molecule of ideal gas, and this molecule of mass M collides with the wall of the gas container along x direction or along x axis. The molecule of mass M is moving with velocity v and with the linear momentum mv along x axis and collides elastically with the wall of the gas container, and as this collision is elastic collision, the same molecule will be reflected back with the same linear momentum mv. mv. Change in linear momentum of this gas molecule along x-axis will be delta P equal minus mv. That means change in linear momentum of this gas molecule along x-axis will be Pf minus Pi, where Pf is the final linear momentum along negative x-axis, that is Pf equal to minus mv, and Pi is the initial linear momentum which is equal to mv. Therefore, delta Px will be minus 2mv. That is the change in linear momentum of the gas molecule as it collides the wall of the gas container along x-axis with the linear momentum mv, and minus mv will be final linear momentum along positive x-axis as it is negative final linear momentum. That's why it will be along negative x-axis. Delta Px is equal to minus 2mv, which is the change in linear momentum of the gas molecule which undergoes elastic collision with the wall of the container, and delta Px prime will be minus delta Px, which is the amount of linear momentum which will be imparted to the wall of the gas container. Delta Px prime is the amount of linear momentum which is imparted to the wall of the gas container. Delta Px prime is equal to 2mv. That is the amount of linear momentum imparted to the wall of the gas container along x-axis. Delta Px prime is equal to 2mv, which is the change in linear momentum. Change in linear momentum imparted to the wall by the gas molecule, imparted to the wall of the gas container by the gas molecule. Negative sign is due to opposite direction of reflected molecule with respect to positive x-axis. Linear momentum changes along negative x-axis. Linear momentum of the molecule changes along negative x-axis. That's why delta Px occurs along negative x-axis, and delta Px prime, which is the amount of linear momentum imparted to the wall, will be along positive x-axis. Therefore, Therefore, the force exerted by this gas molecule on the wall of the gas container along x-axis will be Fx, which is equal to delta Px prime by delta T. Therefore, pressure exerted by this gas molecule along x-axis on the wall will be Px, capital Px, which will be equal to force by area, that is Fx by A. Px, capital Px is equal to Fx by A, which is the pressure exerted by the gas molecule to the wall, and Fx is equal to rate of change in linear momentum, which is the force experienced by the wall as the gas molecule collides with the wall along x-axis. Therefore, the pressure exerted by the gas is due to the continuous bombardment of gas molecules with the walls of the containers. The pressure exerted by the gas is due to the continuous bombardment by the gas molecules against the walls of the gas container, against the different walls of the gas container. Number 3 concept of this chapter is expression of pressure exerted by a gas. Expression of pressure exerted by an ideal gas. We can consider three-dimensional axis, x-axis, y-axis and z-axis. M is the mass of a gas molecule which is moving with a velocity v, and we can consider the three rectangular components or three mutually perpendicular components of linear momentum of the gas molecules. Here Px, Py and Pz are the linear momentum, the component of linear momentum along x, y and z axis, and the pressure exerted by the gas has the expression P equal 1/3 m by v Vrms square. P is equal to 1/3 m by v Vrms square. That is the pressure exerted by a gas, where m is the mass of the ideal gas, v is the volume, and Vrms is the RMS speed or RMS velocity of the gas molecules. In this case, Vrms is the RMS velocity of gas molecules, or root mean square velocity of gas molecules, which is equal to root over v1 square plus v2 square plus plus vn square divided by capital N, where capital N is the number of gas molecules. Vrms is the RMS speed of the gas molecules, RMS velocity or RMS speed of n number of gas molecules. Capital M is the total mass of the gas, V is the volume of the gas, V is the volume of the gas or volume of the gas container. Therefore, pressure exerted by the gas P is equal to 1/3 rho Vrms square. P is equal to 1/3 rho Vrms square. Pressure has the expression that is 1/3 rho Vrms square, where rho is the density of the gas. We can write down the expression of pressure exerted by a gas, and we can assume that pressure exerted by the gas along x-axis, y-axis and z-axis will be equal, and that can be assumed as P. And here P is not equal to Px plus Py plus Pz, but P is equal to Px is equal to Py is equal to Pz. So pressure exerted by the gas has the expression 1/3 m Vrms square, where m is small m into capital N. Small m is mass of each molecule, capital N is the total number of gas molecules. Capital N is the total number of gas molecules. So the expression of pressure exerted by a gas will be 1/3 mn by v Vrms square, and that can be written as 1/3 small m small n Vrms square. M under bracket n by v, capital N by capital V, Vrms square. Therefore, P is equal to 1 by 3 mn Vrms square. P is equal to 1 by 3 small m small n Vrms square. That is the pressure exerted by a gas. P is equal to 1 by 3 small m small n Vrms square, where small m is mass of each molecule, small n is the number of gas molecules per unit volume. Capital M by V is the rho, which is the mass density, but small n equal to capital N by V, which is the number of gas molecules per unit volume or number density of gas molecules. Small n is the number density of the gas molecules. That's why P is equal to 1/3 mn Vrms square. That is the pressure exerted by a gas, in a definite direction. This pressure is the pressure exerted by a gas either along x-axis or along y-axis or along z-axis. Now we can state the kinetic interpretation of temperature. We know that average kinetic energy of translation of n number of gas molecules is Ek equal 1 by 2 m Vrms square, where m is the mass of the gas or total mass of the gas or total mass of the n number of gas molecules. Ek is equal to 1 by 2 m Vrms square, which is the average kinetic energy of capital N number of gas molecules, and we know that pressure exerted by a gas is P, which is 1/3 m by V Vrms square, or comma PV is equal to 1/3 m Vrms square, or comma RT equal, in place of PV we can write RT for 1 mole of gas, which is equal to 1/3 m Vrms square. For 1 mole of an ideal gas, PV is equal to RT. That's why in place of PV we have written RT. And number of gas molecules capital N will be equal to Avogadro's number Na. We get RT as equal 1 by 3 m Vrms square. Therefore, average kinetic energy of translation Ek will be 3 by 2 RT, where capital M is the molar mass, and we get average kinetic energy of translation of 1 mole of ideal gas will be Ek, which will be equal to 3 by 2 RT. Ek is equal to 3 by 2 RT, which is the average kinetic energy of translation of 1 mole of gas. Therefore, Ek prime will be equal to Ek by Na. Ek prime is the average kinetic energy of translation of 1 molecule of the gas, and that will be equal to Ek by Na. And if we put the expression, then we get 3 by 2 under bracket R by Na into capital T, where capital T is the absolute temperature, and R by Na, universal gas constant R by Na is the Boltzmann constant Kb. Kb is equal to, though it is written as K subscript B, but it should be K. K is equal to R by Na, that is Boltzmann constant, and it is written as K subscript B, and we get Ek prime as equal 3 by 2 Kt, where K is the Boltzmann constant. Ek prime is equal to 3 by 2 Kt, which is the average kinetic energy of translation of 1 molecule of the ideal gas. Ek prime is equal to 3 by 2 Kt, and therefore Ek prime is directly proportional to absolute temperature T, and at absolute temperature T equals 0 Kelvin, Ek prime will be equal to 0. Hence the molecular motion ceases at 0 Kelvin temperature, and this is the kinetic interpretation of temperature of an ideal gas. This is the uh, kinetic interpretation of temperature, and at T equals 0 Kelvin, kinetic energy of each molecule will be 0. And this is the kinetic interpretation of temperature. That means average kinetic energy of translation is directly proportional to its absolute temperature, and molecular motion ceases at 0 Kelvin temperature. And if we put the values, Na is equal to 6.023 into 10 to the power 23 mole inverse. Universal gas constant R is equal to 8.31 joule per Kelvin per mole. Avogadro's number Kb is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. RMS speed of gas molecules. RMS speed of gas molecules. So we know the expression of pressure exerted by a gas P is equal to 1/3 rho Vrms square. That is P equal 1/3 m by V Vrms square, where Vrms is the RMS speed of gas molecules, which is equal to root over V1 square plus V2 square plus dot Vn square divided by capital N. These are the different gas molecules, and first gas molecule is moving with speed v1, second gas molecule is moving with velocity v2, and nth gas molecule is moving with the velocity vn. Nth gas molecule is moving with the velocity vn, and gas molecules are moving with different speeds in different directions. That's why Vrms will have another expression, that is root over 3p by rho. Vrms is equal to root over 3p by rho, and also Vrms can be written as root over 3p pv by m, where rho is the density which is equal to m by v, and therefore Vrms is equal to root over 3 RT by capital M. So these are the different expressions of RMS speed of gas molecules. Here M, capital M is the molar mass or mass of the gas, and for 1 mole of gas capital M is the molar mass, and for 1 mole of gas PV is equal to RT, and capital M is the molar mass. Capital M is the molar mass of the ideal gas. So RMS speed has different expression. First expression is Vrms equal root over 3p by rho. Second expression is root over 3RT by capital M equal root over 3 Na k T divided by Na into small m. Therefore Vrms is equal to root over 3 kT divided by small m. Vrms is equal to root over 3 kT divided by small m, where small m is mass of one molecule, K is the Boltzmann constant, though it is written as Kb. Vrms is equal to root over 3 kT by small m, which is RMS speed of gas molecules. Small m is mass of one molecule. Small m is mass of one molecule, where capital M is the molar mass of the ideal gas. Capital M is the molar mass of the ideal gas. Capital R is the universal gas constant. Small m is the mass of one molecule. Mass of one molecule. K is the Boltzmann constant, and it is written as K subscript B. K is the Boltzmann constant, which is the ratio of universal gas constant and Avogadro's number. Vrms is equal to 1.732 times of capital root over capital RT by capital M. Vrms is equal to 1.732 times of root over capital RT by capital M. Number 2. Avogadro's number 2 is average speed of gas molecules. Number 2 is average speed of gas molecules. Average speed of gas molecules. This is a gas molecule of mass m which is moving with a speed v1. First gas molecule is moving with speed v1, second gas molecule is moving with speed v2, and nth gas molecule is moving with speed vn. That's why average speed of the gas molecules will be v1 plus v2 plus vn divided by capital N. That is the average speed of the gas molecules. We know that Vrms is equal to root over 3RT by capital M, where M is the molar mass, but average speed VAV is equal to a root over 8RT divided by pi capital M. VAV equal to root over 8RT by divided by pi capital M, which is the average speed of gas molecules. Which is the average speed of gas molecules. In the expression of VAV, in the expression of average speed of gas molecules, that is VAV, capital M is the molar mass of the ideal gas, capital R is the universal gas constant. From the expression of Vrms, what we can write, from the expression of Vrms equal root over 3RT by capital M, we can write Vrms will be equal to root over 3KT by small m, where small m is the mass of one molecule. Small m is the mass of one molecule. And K is the Boltzmann constant. And K is written as KB. That is the Boltzmann constant. So VAV has another expression, that is root over 8KT by pi small m. VAV is equal to root over 8KT divided by pi small m. And VAV has another expression, that is 1.596 root over RT by capital M. So these are the different expressions of average speed of gas molecules. Number 3, most probable speed. For that, we can consider probability function of finding gas molecules. P under bracket small v is the probability function, that is dn by n. dn by n. N is the total number of gas molecules, and P under bracket V is equal to dn by n, which is the probability, that is the fraction of number of gas molecules, fraction of total number of gas molecules having speed, fraction of total number of gas molecules having speed V, and if we plot probability function, in that case obviously probability function will change with the speed as shown in the graph. That is the probability function versus velocity graph, and this is the maximum probability function that means at V equal V max, probability function will be maximum. That is at V equal V max, P will be P max, and here P under bracket V is a probability function of finding gas molecules. At V equal V max, probability function increases to its maximum value. If V is equal V max, which is the most probable speed, then P tends to P max, and the expression of V max will be root over 2 capital RT by capital M, 2 capital RT divided by capital M. Vmax is equal to root over 2 RT by capital M. That is the most probable speed of gas molecules. Most probable speed of gas molecules. This is the velocity or speed with which maximum number of gas molecules are moving. Vmax is equal to root over 2 RT by capital M is the most probable speed of gas molecules. This is the speed with which maximum number of gas molecules are moving. Vmax is equal to root over RT by capital M, where capital M is the molar mass of the ideal gas. Capital M is the molar mass of the ideal gas. So Vmax is equal to root over 2 kT by small m. Vmax is also root over 2 kT by small m, where small m is the mass of one molecule. That is the most probable speed of gas molecules. Vmax is equal to root over 2 RT by capital M, and also Vmax is equal to 1.414 divided by 2 RT by capital M. So if we write down the expression of RMS speed of gas molecules, Vrms is equal to root over 3 RT by capital M equal 1.732 divide into root over RT by M. V average has the expression root over RT by pi capital M, that can be written as 1.596 root over RT by capital M. Vmax can be written as root over 2 RT by capital M, and which also can be written as 1.414 into root over RT by capital M. So that's why you can say that Vmax less than V average less than V RMS. That means RMS speed of gas molecules has the maximum value, and we can denote RMS speed, average speed, and maximum speed or most probable speed on the graph. So Vmax has a minimum magnitude, and we can denote here V average. V average has the value which lies between Vmax and Vrms, and RMS speed of gas molecule has the maximum value, and Vmax, and we can denote Vmax, V average, and Vrms. The value of Vrms and also V average and Vmax can be denoted in probability function versus velocity graph. Now we can write down the expression of number of degrees of freedom, that is F equal to 3n minus k. F is equal to 3n minus k, where F is the number of degrees of freedom, capital N is the number of atoms in a molecule, capital N is the number of atoms in a molecule, k is the number of common relation or number of constraints, or number of common relations, and F is equal to 3n minus k, which is the number of degrees of freedom. F equal to 3n minus k, which is the number of degrees of freedom. F is equal to 3n minus k, that is the number of degrees of freedom, that is the number of independent quantities to describe the configuration and position of the thermodynamic system. Number of independent quantities to describe the position and configuration. Independent quantities to describe the position and configuration of the thermodynamic system. That is the number of different directions along which internal energy of the thermodynamic system will be uniformly distributed. The number of different directions of a molecule along which the internal energy will be uniformly distributed. The number of different directions of a molecule along which total internal energy of the gas, that is the thermal energy of the gas, will be uniformly distributed. F equal 3n minus k, that is the number of degrees of freedom, that is the number of different directions of a molecule along which the total internal energy, that is the thermal energy of the gas molecule, will be uniformly distributed. Now we can consider diatomic gas, which consists of two atoms. This is first atom and that one is second atom, and we can consider three-dimensional axis with respect to first atom and second atom also. Finally, we get 5 axes for the two atoms because one axis will be common. This is first axis, second axis, third axis, fourth axis, and fifth axis. The amount of internal energy in each direction is half kT. So half kT is the amount of energy or amount of thermal energy in each direction. For diatomic gas, number of atoms in each molecule will be n, capital N. Capital N is the number of atoms in diatomic gas and the value of number of atoms is 2. Now we can denote the common distance between the two atoms. This is the common distance. This is the common distance and the number of common distance is 1 only. K is equal to 1. Number of constraints, that means number of common distance is 1. So we can write K as equal 1. K is equal 1, which is the number of constraints. So number of degrees of freedom F will be what? What will be the number of degrees of freedom? Number of degrees of freedom F will be 5. Because F equal to 3n minus k, which is equal to 3 into 2 minus 1. That's why the number of degrees of freedom F will be equal to 5. F is equal to 5, that is the number of degrees of freedom of a diatomic gas. Number of degrees of freedom of a diatomic gas is equal to 5. Let 100 joule be the internal energy of a diatomic gas and that will be uniformly distributed along each degrees of freedom. There are 5 different directions or there are 5 degrees of freedom and in each degree of freedom the amount of internal energy will be 20 joule. 20 joule is the amount of internal energy along each degree of freedom and we can denote the amount of internal energy along each degree of freedom, that is equal to 20 joule. That is equal to 20 joule. Now we can consider 3-dimensional axis with respect to first atom. These are the 3 axes, that is Z1, Y1 and X1 axis. Similarly, with respect to second atom, we can denote 3 axes, that is X, Y and Z axis. X, Y and Z axis. This is a diatomic gas and the axis X and X1 will be common axis. That's why number of common distance between first atom and second atom will be 1. That is the value of number of constraint will be 1 because X axis is common with respect to first atom and second atom. And we can denote the number of degrees of freedom 1, 2, 3, 4, 5. There are 5 degrees of freedom along which internal energy will be uniformly distributed. If we consider internal energy as 100 joule and that will be equally distributed in each degree of freedom. For monoatomic gas, we can denote the gas atom of a monoatomic gas. This is the atom which has 3 different mutually perpendicular axes, X, Y and Z axis. First, second, third. There are 3 different axes which are mutually perpendicular to each other and number of degrees of freedom F will be equal to 3. F is equal to 3, which is the number of degrees of freedom. That means there are 3 different directions along which internal energy of the gas atom will be uniformly distributed. Number of atoms of monoatomic gas, number of atoms in a molecule of monoatomic gas is 1. That's why n equal to 1. And number of constraints or number of common relation will be 0. Number of constraints, that is the number of common relation, will be 0. That's why number of degrees of freedom f will be equal to 3n minus k, which is 3 into 1 minus 0. That will be equal to 3. That's why the number of degrees of freedom f will be equal to 3. If we consider linear triatomic gas, then there are 3 atoms in a molecule, and we can denote 9 axes for these 3 atoms, Z, Y, and X axis. These are the 9 axes with respect to the 3 atoms in a molecule of linear triatomic gas. And the 3 axes along X axis will be common axis, and these are the atoms, first atom, second atom, and third atom of this linear triatomic gas. This is the linear triatomic gas molecule containing 3 atoms, and we have to find the number of degrees of freedom for this linear triatomic gas molecule. Number of directions along x-axis. Number of directions along x-axis is 1, because the 3 axes along the x-axis are common. That's why the number of direction along x-axis will be 1, because there are common direction along x-axis. Similarly, there will be 3 different z-axis. That's why number of directions along in vertically upward direction will be 3. Number of directions along z-axis is 3. Number of directions along x-axis is 1, but number of directions along z-axis is 3. And number of directions along y-axis is also 3, along which internal energy will be uniformly distributed. That's why the number of degrees of freedom, that is F, will be equal to 7. That is the number of degrees of freedom of a linear triatomic gas molecule. F is equal to 7, for which is the number of degrees of freedom of linear triatomic gas molecule. Here the number of atoms in a molecule is n, which is 3, and number of degrees of freedom F is equal to 3n minus k. And here the value of number of constants, that is k, will be what? We know that this is the first common distance between first atom and second atom along x-axis, and there should be another common distance between second atom and third atom along x-axis. That's why the value of k, or number of constant, will be 2, and we get the number of degrees of freedom F as 7 for linear triatomic gas. If we consider non-linear triatomic gas, we can draw 3 atoms in this way, so that we get linear triatomic gas molecule. This is a diagram for linear triatomic gas molecule containing 3 atoms, which will not exist along a single straight line. This is y-axis. Similarly, we can denote y-axis connecting first and third atom, and also we can denote x-axis. And we can denote vertical axis, that is z-axis, and z-axis for first and second atom of this non-linear triatomic gas molecule. This is the first atom, second atom, and third atom of the non-linear triatomic gas molecule. Number of independent directions along z-axis will be 3. Number of independent directions along z-axis is 3, and number of independent directions along x-axis will be only 1. Along x-axis will be only 1, and that is applicable for third atom. Number of independent directions along x-axis will be only 1, but number of independent directions along y axis will be 2. Will be 2. 3, 1, 2. These are the number of independent directions, so you can denote number of independent directions along z axis. This is the number of independent direction along x axis, and we can denote two different independent direction along y axis. That's why number of degrees of freedom f will be 6, and number of atoms in nonlinear atomic gas n equal to 3, and k is equal to 3. That means number of constant is 3, 1 along x axis and 2 along y axis. K is equal 3, that is the number of constant is 3, because there are two common distance along y axis between the atoms and one common distance along x axis. This is the common distance along y axis between first atom and second atom, and there will be another common distance between first atom and third atom along y axis. F is equal 3 for monatomic gas, and number of degrees of freedom F is equal to 5 for diatomic gas. F is equal to 6 for non-linear triatomic gas. The value of number of degrees of freedom, that is F equals 6 for non-linear triatomic gas, and number of degrees of freedom F will be equal to 7 for linear triatomic gas. For linear triatomic gas. Law of equipartition of energy. Law of equipartition of energy, or thermodynamic energy or thermal energy. Law of equipartition of energy. The energy, that is the internal energy or thermal energy. The energy, that is the internal energy or thermal energy. Thermal energy of a thermodynamic system. Associated, the energy associated with each degree of freedom, is half kT, where k is the Boltzmann constant. The energy associated with each degree of freedom is half kT at absolute temperature capital T, where k, it is written as k subscript b, that is Boltzmann constant. K is the Boltzmann constant, which is the ratio of universal gas constant and Avogadro's number, and k is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. The law of equipartition of energy states that the energy, that is internal energy or thermal energy, associated with each degrees of freedom is half kT at absolute temperature T. Now we can consider the internal energy of a thermodynamical system in terms of degrees of freedom. U double prime is equal to half kT. U double prime equal to half kT, which is the internal energy or thermal energy, associated with each degree of freedom. We are considering the relation between internal energy and degrees of freedom. Now U prime is equal F into U double prime, where F is the number of degrees of freedom. F is the number of degrees of freedom. Therefore, U prime equal half f kt. Half f kt. U prime is equal to half f kt, where f is the number of degrees of freedom of the thermodynamical system, k is the Boltzmann constant, and T is the absolute temperature of the ideal gas in this thermodynamical system. U prime is equal to half f kt, which is the internal energy of one molecule of the gas. U double prime was what internal energy associated with each degree of freedom of an ideal gas, but U prime is equal to half f kt, which is the internal energy of one molecule of the gas. There are f number of degrees of freedom. there are f number of degrees of freedom in each molecules. There are f number of degrees of freedom in each molecule of the ideal gas. That's why what we can write, u equal na into u prime, where na is the Avogadro's number. Putting the expression of u prime, we get na half f kt equal half f under bracket na into k into t, where k equal to r by na. K is the Boltzmann constant. Though it is pronounced as K, but it is written as K subscript B, which is the Boltzmann constant, and Na is Avogadro's number, that is the number of molecules in 1 mole of gas, which has the value 6.023 into 10 to the power 23 mole inverse. Na is equal to 6.023 into 10 to the power 23 mole inverse, which is Avogadro's number. Finally, we get U as equal half FRT. U as equal half FRT, which is the internal energy, of 1 mole of gas, where capital R is the universal gas constant. Capital R is the universal gas constant, which has the value 8.31 joule per Kelvin per mole. U is equal to 1 by 2 half FRT, which is the internal energy of 1 mole of an ideal gas. Internal energy of 1 mole of an ideal gas. 1 mole of an ideal gas, internal energy U is equal to half FRT, and 1 mole has any number of molecules. 1 mole has any Avogadro's number of molecules. Now, for 1 molecule of the ideal gas, internal energy U prime is U divided by Na, which has the expression half FKT, and we know that it has f number of degrees of freedom. 1 molecule has f number of degrees of freedom. That's why internal energy of 1 molecule of gas U prime will be half FKT. Now, for 1 degree of freedom, internal energy will be U double prime, that will be half KT. U double prime is equal to half KT, that means U prime by F, which is equal to half KT, that is U double prime is equal to 1 by 2 KT, which is the internal energy in each degree of freedom. We get the amount of internal energy for 1 mole of gas, for 1 molecule of gas, and for 1 degree of freedom. First law of thermodynamics. For that, we can consider a gas vessel containing an ideal gas having pressure P, volume V, absolute temperature T, and internal energy U. And this is the ideal gas enclosed by a gas vessel, and the gas absorbs dq amount of heat energy, and final state of the ideal gas will be what? Pressure remains constant P, volume changes to V plus dV, temperature changes to T plus dt, and internal energy changes to U plus du. Here we have considered that pressure remains constant and the ideal gas absorbs dq amount of heat energy, and according to first law of thermodynamics, dq is equal to du plus dw. dq is equal to du plus dw, that is amount of heat energy absorbed by the gas will be equal to increase in internal energy, that is du, plus work done by the gas, that is dw. dq is the amount of heat energy absorbed, du is the amount of internal energy or increase in internal energy, and dw is the work done. That is the first law of thermodynamics, and we get du. du is the change in internal energy or increase in internal energy if the gas absorbs dq amount of heat energy. du is change in internal energy of the ideal gas. dw equal work done by the gas if it absorbs dq amount of heat energy. dw equal work done by the gas. If the pressure under bracket p remains constant, if the pressure of the ideal gas remains constant, then work done dw will be equal to p dv, and dv is the change in volume of the gas, or dv is the increase in volume of the gas provided the gas absorbs dq amount of heat energy. Therefore dq will have the expression du plus pdv. dq is equal to du plus pdv, which is the expression of first law of thermodynamics. dq is the amount of heat energy absorbs, du is increase in internal energy or change in internal energy, pdv is the work done, where dv is the increase in volume or change in volume of the ideal gas. Now we have to know the formula of molar specific heat of the ideal gas at constant volume. Molar specific heat of the ideal gas at constant volume, which is Cv, capital Cv, is equal 1 by n dq by dt under bracket subscript V. Capital Cv is the molar specific heat of the ideal gas at constant volume, which is 1 by n dq by dt V. That is the molar specific heat of the gas at constant volume. It is capital Cv or C in uppercase. C subscript V. Cv is the molar specific heat of the ideal gas at constant volume, where dt is the change in absolute temperature of the ideal gas, and dq is the amount of heat energy absorbed by the gas, or the change in heat energy of the gas. dt is the change in absolute temperature of the gas due to dq amount of change in heat energy. N is the number of moles of the gas or amount of gas. Unit of molar specific heat of the gas, that is unit of Cv, is joule per Kelvin per mole. Unit of Cv or unit of molar specific heat of the gas at constant volume will be joule per Kelvin per mole. Small Cv is the specific heat of the gas, which has the expression 1 by mt dq by dt V, where mt is the total mass of the gas. It is not the molar mass. mt is the total mass of the gas. And small Cv is only the specific heat of the gas at constant volume. Small Cv is equal to 1 by mt dq by dt subscript V. That is the specific heat of the ideal gas at constant volume, and it is denoted by small Cv. Now we know that capital Cv is equal to capital M into small cv. Capital Cv is equal to capital M into small cv, where capital M is the molar mass of the gas. Capital M is equal to mt, that is total mass, divided by number of moles, which is the molar mass, mass of the ideal gas. Molar specific heat of ideal gas at constant pressure. Capital Cp is equal 1 by n dq by dt subscript V, subscript P. Cp is equal 1 by n dq by dt P, which is the molar specific heat of the ideal gas at constant pressure. But small Cp equal 1 by mt dq by dt P. Small Cp is the specific heat of the ideal gas at constant pressure. Therefore, capital Cp is equal capital M into small cp, where capital M is the molar mass of the gas. Capital Cp is equal 1 by n dq by dt P, which is the molar specific heat of the ideal gas at constant pressure. Capital Cp is the molar specific heat of the ideal gas at constant pressure. But small cp Small cp small cp is equal to 1 by mt dq by dt v, that is the specific heat of the gas at constant pressure. Specific heat of the ideal gas at constant pressure. And capital Cp is equal to capital M into small cp, where capital M is the molar mass of the gas. Now you have to mention the relation between Cp and Cv. Gamma is the ratio of molar specific heat of the gas at constant pressure and volume. That means gamma is equal to Cp by Cv. And also Cp minus Cv is equal to R, where R is the universal gas constant. Cp minus Cv is equal R for 1 mole of gas. That means difference between molar specific heat of the gas will be equal to universal gas constant R. Cp minus Cv will be what for in mole of gas? We know that Cp minus Cv equal to R for 1 mole of gas. So what should be the value of Cp minus Cv for n mole of gas? Here Cp minus Cv will be equal to R. That will be again equal to universal gas constant R. Cp minus Cv is equal to R for n mole of gas. Now you have to know the expression of molar specific heat of an ideal gas in terms of degrees of freedom. Molar specific heat of an ideal gas in terms of degrees of freedom. We know that capital Cv equal 1 by n dq by dt subscript v. That means molar specific heat of the ideal gas at constant volume. For n equal 1, that means for 1 mole of gas, for 1 mole of the ideal gas, number of moles, that is n equal 1, therefore Cv will be equal dq by dt subscript v. According to first law of thermodynamics, heat absorbed by the gas, heat absorbed by the ideal gas will be dq equal du plus p dv. Therefore dq will be equal to du plus 0, since dv is equal 0 at constant volume. That means at constant volume, change in volume will be 0. That means if volume is kept constant, change in volume will be 0. That means dv will be equal to 0. Change in volume under bracket dv is 0. Therefore dq is equal to du. That means change in heat energy will be equal to change in internal energy of the gas. Therefore Cv, the expression of molar specific heat of the gas at constant volume, will be Cv. And here dq is equal to du, that is the heat absorbed by the ideal gas, and du is the increase in internal energy of the gas. Du is equal to increase in internal energy of the gas. Therefore Cv is equal to du by dt, rate of change in internal energy of the gas with respect to its absolute temperature, which will be equal to Cv. We get Cv as equal to du by dt, which is the molar specific heat of the ideal gas in terms of internal energy at constant volume. Cv is equal to du by dt equal ddt of u ddt, and we know the expression of internal energy, that will be u, which is equal to half F(T). For 1 mole of gas, internal energy u is equal to half F(T), where F is the number of degrees of freedom. That's why ddt half F(T). We get Cv as equal half Fr ddt under bracket T, bringing half Fr outside ddt. Therefore Cv will be equal to half Fr. Cv is equal to half Fr. That is the expression of molar specific heat of the gas at constant volume in terms of degrees of freedom. Cv is equal to half Fr, which is the molar specific heat of the ideal gas, in terms of number of degrees of freedom F. Cv is equal to half Fr. That is the expression of molar specific heat of the gas at constant volume. Molar specific heat. Molar specific heat of an ideal gas at constant pressure in terms of degrees of freedom. What should be the expression of molar specific heat at constant pressure in terms of degrees of freedom? We know that Cp minus Cv is equal to R. Therefore, Cp is equal to Cv plus R. Putting the expression of Cv, we get Cp as equal half Fr plus R. That means half F plus 1 bracket closed into capital R. That is the expression of molar specific heat of an ideal gas at constant pressure in terms of degrees of freedom. Now, the ratio of molar specific heat of the gas at constant pressure and volume is gamma, which is Cp by Cv, is equal half F plus 1 R divided by half Fr. And what should be the expression of gamma in terms of number of degrees of freedom? Now simplifying, we get what? Simplifying, we get F plus 2 divided by 2 whole divided by F by 2, and we get gamma as equal to 1 plus 2 by F, gamma as equal to 1 plus 2 by F. That is the expression of ratio of molar specific heat of the gas. Gamma is equal to 1 plus 2 by F. That is the ratio of molar specific heat of the gas at constant pressure and volume in terms of number of degrees of freedom. From the above equation, we can write 2 by F as equal gamma minus 1. Therefore, F is equal to 2 divided by gamma minus 1. F is equal to 2 divided by gamma minus 1. That is the number of degrees of freedom. That is the number of degrees of freedom of an ideal gas in terms of gamma. That means in terms of ratio of molar specific heat of the gas at constant pressure and volume. F is equal to 3n minus k, and U is equal to half Frt, and Cv is equal half R. Half Fr, these are the important formula in this topic. Now we can make a table for different types of gas having values of degrees of freedom and ratio of molar specific heat. Monoatomic gas, diatomic gas, non-linear triatomic gas, then linear triatomic gas. That is, we have to consider monoatomic gas, diatomic gas, non-linear triatomic gas, and linear triatomic gas. Degrees of freedom under bracket F. Degrees of freedom under bracket F. The value of number of degrees of freedom for monoatomic gas is 3. The value of number of degrees of freedom for monoatomic gas is 3. Then we have to know the expression or value of Cv, Cp and gamma. Cv, Cp and gamma. What will be the value of Cv? Cv has the expression half Fr, and Cp is equal to Cv plus R, and gamma is equal to Cp by Cv. Gamma will be equal to Cp by Cv. The value of Cv for monoatomic gas is 3 by 2R, and the value of Cp is 5 by 2R, and the value of gamma will be 5 by 3, that is 1.67. For diatomic gas, the value of number of degrees of freedom will be 5. For diatomic gas, the value of number of degrees of freedom will be 5. F is equal to 5, that is degrees of freedom for diatomic gas is 5. The value of CV is equal to 5 by 2R, as CV is equal to half FR. Value of CP is 7 by 2R, and gamma is equal to 7 by 5, which is 1.4. And for non-linear triatomic gas, the value of number of degrees of freedom, that is F, will be equal to 7. F is equal to 6, not 7. For non-linear triatomic gas, the value of degrees of freedom will be 6. F is equal to 6 for non-linear triatomic gas, and the value of CV will be 3R. Value of CP will be equal to 4R, as CP is equal to CB plus R, and value of gamma will be equal to 4 by 3, which is 1.33. These are the values of different quantities for non-linear triatomic gas. Similarly, for linear triatomic gas, the number of degrees of freedom F will be 7. CV is equal to 7 by 2R, CP is 9 by 2R, and gamma is 9 by 7, which is 1.28. The ratio of molar specific heat for linear triatomic gas will be 9 by 7, which is 1.28. Now we can compare the expression of kinetic energy of translation of gas molecules and internal energy of gas molecules. Ek is equal to 3 by 2 RT, whereas U, that is the internal energy, is U, which is equal to half FRT. U is the internal energy of an ideal gas, which is half FRT. Internal energy of an ideal gas at absolute temperature T in terms of degrees of freedom F. U is equal half FRT, which is the internal energy of 1 mole of an ideal gas in terms of degrees of freedom, whereas average kinetic energy of translation of 1 mole of gas is Ek, which is 3 by 2 RT. Ek is equal to 3 by 2 RT, which is the average kinetic energy of translation. Average kinetic energy of translation of 1 mole of ideal gas. 1 mole of ideal gas. Average kinetic energy of translation Ek is equal to 3 by 2 RT. Whereas internal energy of 1 mole of gas is equal to 3 by 2 RT for monoatomic gas. U is equal to 3 by 2 RT, that is the internal energy of 1 mole of monoatomic gas. And U will be 5 by 2 RT. U will be 5 by 2 RT, that is the internal energy of 1 mole of diatomic gas. U equal to 5 by 2 RT, that is the internal energy of 1 mole of diatomic gas. And left hand side Ek is always 3 by 2 RT, that is the average kinetic energy of translation for any type of gas. Ek is equal to 3 by 2 RT, that is the average kinetic energy of translation of 1 mole of monoatomic or diatomic or triatomic gas. Average kinetic energy of translation has the same formula for any type of gas, but internal energy will have different formulae for different types of gas.